Thank you very much. I'll just make sure I've got things lined up here. Okay, great. So thanks to the BMCAA for the opportunity to present. And also in terms of land acknowledgement, I want to say that I'm on the west coast of BC. I live on the traditional territory of the Coast Salish, Songhees, and WSÁNEĆ. So October, make sure, go forward. Okay. October was Breast Cancer Awareness Month. And in the spirit of that, I collaborated with another YouTube channel called Unpacked, which is a channel about Jewish life, history, and culture. And I mean, I'm not Jewish myself, but I am on board with promoting public health. And that's the topic of the video that we worked on together. There's a high incidence of breast cancer or BRCA1 and 2 gene mutations in Ashkenazi Jews in particular. So it's important to be aware of one's family history and your level of breast cancer, et cetera. My piece of the video was a very brief explanation of the BRCA genes. So I'm going to play that here now. Hopefully the audio, oh, you know what, just let me check. Did I don't know if I shared the, no, I didn't share my video sound. So there we go. Let's try this now. Okay. And maybe after.
And while both genes have similar names, they actually aren't directly related, as each is a mutation of a different chromosome. When one or both of these genes are mutated, they are no longer able to prevent tumors from forming, which means that there's an increased risk of breast cancer, as well as ovarian and pancreatic cancer, among others.
Okay, so that was it. And if you didn't hear the narration, just send a little message in the chat and I can explain what the point of all of that was.
And while both genes...
We'll move forward.
And while both...
Okay, at this moment in the animation, I wonder if anybody noticed anything in particular about, thanks Alex, the structure of this DNA with respect to the BRCA genes in particular. That's right, I used the actual gene sequences for BRCA1 and BRCA2 in these DNA structures. Did anybody notice that? Okay, nobody noticed that. Even a genetics expert in BRCA genes would not notice that. How could they? Therefore, nobody would be troubled if I use just a random sequence of bases, right? Does anybody think it's cool that I used the actual DNA sequences in this DNA structure? Maybe. Okay, well, here they are, the DNA sequences I used. There's a point to be made here, which is, when does data matter? And I'm using data as a shorthand for like all kinds of science information, not just like numbers and stuff. In every project, there are dozens of decisions to be made about how or whether you use different kinds of information to make your visuals. And often it might look something like this. You can either choose to use something made up, something maybe patterns or random textures or an artistic impression, or basically just something that looks good, right? Or possibly there might be experimental data you can use, visual references, literature, research, and basically anything you look up, right? Either look it up or you make it up. And I'm not saying one or the other is right all the time. Obviously things, both of them are important at different times. So I'm going to go out on a limb and say that the answer to that is usually, and in retrospect, I kind of walk that back. I'll say often based on two competing factors. There's this decision-making process, this kind of calculus between the effort that's required to use data, information, versus how much that information adds to your visualization and your communication. Now, effort could be measured in terms of like your own knowledge gap, whether you know something, the availability of that information, how easy it is to translate that data into your visuals, et cetera, et cetera. Now, for the primary learning objectives of your piece of communication, obviously the scientific data is key, like that outweighs anything else. The benefit is like, that's the entire point of the thing. So that obviously takes precedence. But I mean, for example, you can't show an anatomical structure without having some kind of sense of the reality of what that structure looks like. Beyond that, though, it gets messy, right? It's the decision-making process is a little bit more nuanced. Basically, one option is if the effort is very minimal to use data and there's some measurable benefit. If it's just as easy or easier to use some reference than just making something up randomly, well, then you want to do it, right? So for my case, this animation here, one of the things I had to make was a karyotype, different chromosomes. And so I had to think, okay, I need to model these chromosomes, 20 to 23 different ones. How important is it for these to be the right size, right? The right length. And I think that's pretty important. Obviously, you want chromosome 1 is the longest, so we should show it that way. And chromosome 22 is the smallest, so we should show it that way as well. Is it easier to make up some random shapes than to do it properly? I mean, it's not that much different, actually. You can just find a picture of a karyotype and model one chromosome, duplicate it a bunch of times, and kind of pull vertices around or stretch it out or whatever to make the approximate proper size. In my case, it was even easier to use the data directly, which is one of the big reasons why I really love Houdini. Because what I did was I downloaded just a text file of the lengths of each arm of each chromosome, just brought that into Houdini, and I could create the relative sizes very easily. The point is, why make it up if the data is right there and you can use it? So I modeled the chromosomes, made them wiggle around a little bit. Job done, kind of. Then in other cases, you're kind of going back and forth a little bit more. So you start thinking about, well, is anybody going to notice? Are there people that are going to be caring about this particular aspect of something? Somebody might have a pet peeve and you're going to get a, well, actually, which never feels good. But it also gives you a good feeling to know that you've kind of presented something as accurately as you can, right? There's that internal satisfaction, even if nobody else notices. So you're trying to gauge how hard is it going to be to match reality, how clearly anybody actually knows what that reality is like, if there's scientific consensus, and versus how easy it is just to slap some kind of thing on it, just random values or some random texture. So my example for this is the chromosome banding that is on chromosomes. Now, I thought this might be a way to add some visual interest to the chromosomes, kind of sell the idea that they are chromosomes, and also just to show that there's sort of different positional places where genes can be on the chromosome. It goes by quickly. It's not strictly necessary. The banding, it's not like a visual thing in the cells. It's kind of like a staining process. But I did know that that staining process is consistent across humans. So I wondered if there was data for that. And indeed there is. I downloaded another text file, brought it into Houdini using pretty much the same kind of approach, because I could map it to the same lengths as the chromosomes. The bases all line up. And I could texture the chromosomes based on that staining to show the bands. So not too crazy difficult. And it gives me a little bit of confidence and peace of mind in my visualization that I was doing something kind of properly, as it were. Now, of course, if the data or reference is not available, then you have to make something up. You have to use maybe a random values or random colors or random shapes or whatever it might be, something that looks good, something that's aesthetic, because there's nothing to get at, or maybe it's too difficult to get at the information you're looking for. There's limits, right? There's time limits, etc. So in my case, I noticed in some of the micrographs that there are some sort of grooves around the chromosomes, and I wanted to incorporate that into the visuals because I thought that looked interesting and realistic. But as I dug into it, I couldn't find any concrete information on those grooves, whether they're conserved or whether they're pathogenic or whatever. I found out that there might be called circumferential grooves, but that was kind of as far as I could get within the time that I had. So I just made the chromosomes vary in width a little bit, just to add a little bit of visual variation, and just called it a day. And I think that's fine, right? So we get back to the DNA sequence. Now, I know when I was doing the initial sort of information looking around at the beginning of the project, so on Wikipedia, I looked at the BRCA gene, good starting point, right? And I could see here that there's known mutations in Ashkenazi Jewish populations. There's one in particular, 185, a deletion of the bases A and G. So I was like, okay, so that would be cool to then I can know that I'm deleting 2 bases when I'm showing this mutation, right? So I kind of want to get that right, even though, yeah, maybe it might not matter too much. And yeah, so this is what I wanted to show. So show the bases being deleted as part of the founder mutation, even though it goes by very, very quickly, to show the mutations as accurately as I could. So in a previous animation, which is on YouTube, you should check it out. It's called Lettuce Has a Lot of Protein and Carbs. I developed a DNA tool, and the DNA tool, basically you can either give it tell it to use a random sequence of bases, or you can give it a specific sequence, you know, ATG, TTA, CG, whatever, and it will generate the DNA for that. So now here I'm at decision time, right? I know it would be super easy to just randomly generate bases and show the deletions happening on wherever, somewhere in the middle. But I figured it would be pretty trivial to find that BRCA gene sequence and put that around the relevant mutations, so I know that I'm deleting the right bases. That should be trivial. Super trivial. Very trivial. So what's the first place you go? Again, I went back to Wikipedia and I looked up these. So I wanted to show 185 del deletion of AG, and in bracket 2, there's a 6,174 deletion T. So presumably that's the position that those bases are in. At position 185, there's an A and a G, and that's what has been deleted and the mutation. Likewise, at position 6,174, there's a deletion of T. But the obvious question is the 185 position of what? Like where, like, is there a gene sequence that has that specifically? Hopefully. I used to work as a bioinformatician before BMC, so I know where to find DNA sequences, not a problem. Go to NCBI, search for BRCA1, and I get this page with lots of information, and you can get genomic sequence data. Okay, looks good. So there's a primary assembly and a ref-seq gene. This is what the primary assembly looks like. And I'm looking at this and I'm thinking, okay, and then there's also the ref-seq gene, which is a different sequence, and they probably start at different places. And now I'm starting to feel a little bit out of my depth. And spoiler alert, neither of these has the right bases at the right position. So I know this is not the data that I'm looking for. So stop. Stuart, at this point, you know what to do. You say, screw it, I tried, doesn't matter, just use a random sequence. Most people, when they show DNA sequences, they don't even bother to use different bases at all. It's just like the twisted ladder thing, right? But my brain doesn't let go of problems, which in itself is its own problem. But anyway, it's good that I continued with this, because now I can give an UnCon talk for you. So I went to Discord, biologist Discord called BioCord, and I posted, so if a mutation has this thing, 185 AG, how would I find what sequence that refers to that surrounds that? Like, what's that referring to? No answer, so I keep looking. I go to the Wikipedia references, and one of these references is this tiny little paper, Tonin 1995. And obviously it doesn't have any DNA sequence data. So I look at it and I go, okay, well, let's try somewhere else. So I go back to the first paper that I had found. The free text was available to me. And I looked at that, and sure enough, in there, they show these deletions, different deletions with references, Simard, Friedman, Newhausen, 1996, et cetera. I'm like, okay, so I've got somewhere to look. So I look up Simard, and I go to Nature Genetics, and I find the paper, and I see rent or buy article, $9. So I have some options for research procurement. I should be able to access it through an institution, except that I'm not affiliated with an institution at the moment. I don't have institutional access. I don't even have alumni access. I looked into it. It doesn't give you access to online databases and all that sort of stuff. Not a thing. So when you're working in a pharmaceutical, or in a client relationship with like a pharmaceutical client or a researcher, or somebody, typically they will have access to literature databases, and you can send them an email and say, hey, could you maybe get this paper for me? It has some information that I'm trying to look for. Maybe wait for a while for them to get back to you. But I'm not in a client relationship either, so that's not an option for me. Of course, I could pony up the cash and spend the $9. It's not too bad. Or I could email the corresponding author or look them up on ResearchGate and ask them for the full text and wait maybe 2, 3, 10 days to maybe hear back, maybe. This is research from the 90s, right? Where are these people now? I don't know. And I don't have time for that. Or I could steal it. So what did I do? I did none of those things. I went looking for a different paper. So I looked back at this tone in 1995 and I found a reference to Miki 1994. So I go looking for that. Science, get access, purchase digital access, $30 US. So I decided to pirate it. So for those uninitiated, Sci-Hub is a website that was created by one person, Alexandra Elbakian. She's the only person who continues to maintain it and develop it for security purposes. And this website does one thing and it does one thing only. You put in a URL to a paper or a DOI, a specific DOI reference, and you get a PDF. That's it. It's shockingly simple. Even if you had, like, if it was an open access website, often it's a whole bunch of different clicks to get something. This is just like 2 clicks, click save, you've got the PDF. So Miki, 1994. So I find out that I'm looking for full-length BRCA1 cDNA. For those people that don't know what cDNA is, it's not genomic DNA, it's DNA that's been developed from mRNA. So it's already got the intron spliced out. So it's a specific, different kind of sequence. So I post back on BioDiscord, I trace this to 1994, looks like I'm searching for cDNA sequence. And then this bioinformatician, I think this guy's a bioinformatician professor. I've had a previous conversation with this person. He says, yeah, I hate that nomenclature, referring to the 185 del AG, because if the gene annotation changed, you're screwed. You got to find the cDNA from 1994. So I'm thinking like, that's kind of discouraging. 1994, people didn't have the internet. Where did they put DNA data? Like, there's databases, maybe. I don't know how computers worked in 94. Well, it kind of did, but you know what? Like, what was the standard practice? Did they put accession numbers in papers? Was that typical? Or yeah. So I'm really looking for an accession number in the papers. So I keep looking. Turns out that that paper did have the accession number in it, but for whatever facepalm reason, I didn't find it. I couldn't locate it. No matter, I go back to Tonin. Another reference, Shattuck Idens, 1995. Cool. All right, access to your institution, can't do that. Buy article, $30. Hello, Sci-Hub. So I get that article, and finally, I find the BRCA cDNA sequence in GenBank under accession number U-14680. Success. I found the number. I can go back to NCBI, put in the accession number, and get phytothoracinomomy, which is mold. Doesn't have breasts, let alone breast cancer genes. So at this point, I really should give up, right? But I don't. I have one more idea. I take the hyphen out of the accession number. There we go. BRCA, mRNA, complete cDNA sequence. There's the DNA sequence, and there's the bases that get deleted in that mutation. I take that, bring it back to my DNA tool, put that sequence in, and it looks pretty much exactly the same as it did before. So should I carry on with BRCA2 or leave it at that? Of course I should continue. I go back, Newhausen, 1996. I managed to find Newhausen 1998 as open access. That leads me to Newhausen 1996, $9, Nature Publishing Group. Sci-Hub again. That leads me to Tavtigian 1996, $9 again, Nature Publishing Group. Back to Sci-Hub. And at last, I get GenBank accession U43746, and I get the mRNA cDNA sequence for BRCA2, and there at position 6174 is the T that I need to delete. So there we go. I have my DNA. I have my DNA sequence. I have my beautiful mutation animation. And that's the end of the saga. So you can laugh at me, whatever. That's fine. But hang on. Forget all this DNA sequence stuff. Let's think about the process here. What if that was a mission critical piece of information? Let's say there's no Sci-Hub, There's no, or I stick to my moral code. I don't want to pirate, steal anything. How is a researcher, or a freelancer, I should say, supposed to track down information at a reasonable cost in a reasonable amount of time? This stuff is buried. And if I paid for all those papers out of pocket, that's over $100 Canadian. There's not a chance I can do that, especially because there's no way of me knowing if the information I'm looking for is even in there. Often you're looking for a specific piece of data, but it's really difficult to know from the abstract or the title if that bit of data is actually going to be in those papers or where to find it. Ironically, the gene sequences were freely available the whole time. I just didn't know how to access them. I needed the accession numbers. Another way to think about this is that we are in, as science people, with humanity, we're kind of in a battle, in the middle of a battle between scientific information and misinformation. When's the last time somebody paid for misinformation? Misinformation is free. Not only is it free, it's everywhere. It's in your face. It's getting crammed down your throat. You can't avoid it. And people aren't paying for it. But getting to the truth is stuck behind paywalls, endless roundabout searching and reading and investigating and paying for research articles. It's a really difficult place to be. I've spent a little bit of time, thinking about the debate between like open source publishing versus closed publishers, paid, all of that sort of stuff. Really, it's so complicated. There's so many factors. It's really hard to make a fair, intelligent argument. And I'm not going to do that here. There's, institutions, how they pay for, how the publishers work, how, the information editors, peer review process, all of that. Like, it's very complicated. But we can't just like start and stop with Wikipedia. It's a good starting point, but that's rarely enough. So let's go back to the beginning of my presentation, talking about effort versus benefit. Look at the scales here. When the effort, the time, the money, the mental energy, whatever it is, required to harness real data, scientific information, is high, we don't use it, like for good reason. It's not sustainable. It's not practical. So for me, the honest truth is that Sci-Hub dramatically changes that calculus for me, the decisions weighing the ease of access to data versus just making something up. So there's so much research at my fingertips with it that I can justify, okay, maybe not with that DNA sequence example, but so many other things I can justify looking at tons of papers to find the thing that I'm looking for. And for those of you who think that maybe I spent like days on this, it was really only 40 minutes at the most between when I thought of looking for the sequence to having both sequences available. I went through 8 papers very quickly, and I could have done it more efficiently, but like, that's the research process. You just go through as many different things as you can. You're skimming, you're looking. So when the science is easier to find, our creations benefit, our science communications benefit. They're more informative, they're more accurate. The audiences benefit because they're getting more from it. Everybody wins. The scientists win. Their research is getting out there. Everybody wins except for Elsevier and Springer, the giant conglomerates with billions of dollars in revenue. So I hope that we'll get to a future where all research is truly free. But for now, here we are. I think that Sci-Hub is good for science illustration, animation, visual communication. Do I recommend you use it? Officially, no. Legally, no. And you do need to be careful. The website is constantly under attack. There's legal battles all the time. The domains are getting taken down, so they're getting put up with different names. You can't just go to the old domain. It's risky, right? I'm not recommending it. For the present, using Sci-Hub is piracy in most countries, all countries that I know of. However,
perhaps on the rare occasion pursuing the right course demands an act of piracy. Piracy itself can be the right course.
Thank you everybody for listening to my talk. Again, I don't condone using Sci-Hub officially. And the people that I collaborated did not know that I use Sci-Hub, so they are under no legal whatever. All right. Are there questions?
Thanks so much, Stuart. I think, yeah, officially, the BMCAA does not endorse the use of any unofficial means of collecting information, but you brought up a really interesting, timely kind of topic, and I think it's worth a bit of debate, actually, in conversation. So just running through the comments here, Kevin Wee says, Hollywood would adapt your 40-minute story into a 3-hour movie saga. Feel that.
Man, let's get something up on the internet. That would probably be pretty boring.
And Mesa says, also, once you make a decision, you become a point for other researchers. One bad fact can spread throughout science sources on the web like a virus. Better to get it right for everyone. Yeah, I think it's, again, an interesting conversation for us as science visualizers. What's our responsibility for really representing things accurately, even down to that little mutation that may, in the grand scheme, not seem so critical, but it's sort of a principle, I suppose.
Mm-hmm.
Any questions from the audience?